All right, on to question 2015, question 2. This one was an energy momentum sort of problem. All right, so, oh, wow, I can actually alter the page. Interesting. All right, so this one. It wants us to determine the speed of the dart just before it strikes the block. Well, the thing that's really important about this is the fact that it collides. Where does it say it? Um, yeah. The moment it reaches its highest point of the path, it collides with and sticks to the block. So that's the thing that's important. The fact that when it reaches its maximum height, right here. Now you should remember that for a projectile, two things happen at max height. The first is that the vertical velocity is 0. Always. The vertical velocity is always 0. And that the horizontal velocity is constant. We still have the horizontal velocity that's equal to whatever the initial was. In this case, and remember that in the horizontal direction, it's constant because there is no acceleration. No acceleration in the x. So, all I have to do to figure out what the speed of the dart is just before it strikes the block is just say, find the horizontal direction, so the velocity, let's just do this, 10 meters per second, 30 degrees. This is the y, this is the x. Well, the x component is just going to be 10 cosine of 30. Plug the numbers in, and you should get 8.7 meters per second. And as you probably would have guessed, this was a 1-point answer for that. Now, the one thing that you should really, again, and I know I keep saying this, but stress it enough that with these questions, they all feed into the next. So this velocity that you get here is going to be used later on. It's going to be used in part B. It's going to be and the answer in part B is going to be the answer used in part C, used in part D, yada yada yada. So if you're ever stuck on, especially on this problem, at any point, make up an answer and use that later on, and you will get the points for those questions. Now for this one, calculate the horizontal distance between the launching point of the dart and the point on the floor directly. So basically, what's D? Alright, well first, I need to figure out, because if I look at my chart, let's try and make this chart. It's been a while since we did this. X0, X, B0, B, A, T. Oops. Put that there. Alright, in the X direction it's 0. In the Y direction it's negative 10. I'm dropping my units because I can. You guys cannot. It starts at 0 and 0. It reaches a max height of who knows. Goes the distance D that we're looking for. It has an initial horizontal speed of 8.7. Now I can do it real quick. The y is just 10 sine of 30. So that means that in the y direction, the initial vertical speed is 5. This is 8.7 meters per second. Now the one thing that you should note is this, the fact that this is a positive 5 and this is a negative 10. It's important. It's important that they both have different signs. Now notice, I can't find anything in the x direction. I can't find this until I find time. And the only way I could find time is by looking at the y direction. So, let's see, which one can I use? Oh,
wait, I forgot the most important thing, that the final velocity is 0. There we go. Now the right equation is popping out of my head. V equals V0 plus AT. You might have been able to get away with using the annoying x equation, but that probably would have been really tricky because you would have had to do some sort of actually, you wouldn't have been able to find that distance. You would have had to use timeless first, and then use the magic t, and then you would have had to do a quadratic. Basically, so messy. This one is much more quicker. So 0 equals 5 minus 10t. T equals 0.5 seconds. Use that here to find d, so I can use annoying x. Plus v0t plus 1/2 at squared. 0, 0, x equals 8.7 times by 0.5. X equals 4.4, about. Alright, 2 points for this, 1 point for figuring out the time, and 1 point for basically substituting in correctly and getting the right answer. So this whole thing is 1 point, and this whole setup is getting 1 point. Alright, now this. Calculate the speed of the block after the dart strikes. Now if you look here into the problem here, it says collides and sticks to the block. So it's colliding and sticking, and we want to know what the speed is after. Well, that's just momentum. Initial equals final. That the dart and its initial speed is equal to the dart block final. So the final speed of the whole thing is just going to be equal to the dart's mass over the total mass times the initial speed. Alright, so let's see. 0.02, 0.02, 0.1, and the initial speed was, the speed right before, you remember, it was 8.7, so 8.7. Plug all those numbers in, let's see, move some things around. 8.7, so it's basically 8.7 divided by 6, which is 1.4-ish. So V equals 1.4 meters per second. This was 3 points. 1 point literally for stating this equation. I cannot stress this enough that when you do these problems, you have to make sure that you state conservation of momentum or conservation of energy, especially for a problem like this. You get 1 point for stating this equation and then using it later on. So then you get a point for this, and then you get a point for the substitution and the answer. Alright, so this equation is not enough. You have to state this. I know it's simple, but it gives you points, so why not do it? Alright, now they want us to find the angle at which the dart and block on the string will rise before coming to rest. Alright, now this one's a little bit trickier. So, first, let's see how we want to do this. So we have a block going from here to there. It's going from moving down here to being at rest here. Somewhat like a pendulum. So what we want to do is use conservation of energy. Kinetic here, potential here. They should be equal. So I do kinetic plus potential equals kinetic. Kinetic equals potential. 1/2 mv squared equals mgh. Masses drop out. The height is just going to be v squared over 2g. We said that the velocity was 1.4 squared over 20-ish. 1.4 squared. I have no idea what that is. It's something. Alright, so this height is going to be about 0.098 meters. Now I'm just going to round it to 0.1 meters. Alright, now that right there will get us about 2 points, I would say. Probably 1 point for realizing that we had to do conservation of energy, and 1 point for finding out how to get the height. But in order to get the full 3 points, the next part is to figure out what the angle is. Alright, well, I just found out the height. How high this ball reached. Now that I draw like this, maybe you can see what I'm probably going to be doing. In order to find this angle, I need to know what this is and what this is. So, cosine adjacent over hypotenuse. It's the easiest ones to find. The hypotenuse, I already know this, not to be confused with h, the height. That's the hypotenuse, and this is adjacent. Well, the hypotenuse we know is the length of the string, 1.2 meters. The adjacent, though, isn't the full length of the string. It's the length of the string minus how high it rose, 0.1. So we end up getting 1.1 divided by 1.2. Plug and chug, and you get 24 degrees. And you get your last point there. We're doing all this. Alright. Again, the trickiest part was realizing that, but that's something that you realize from experience. I've seen this type of problem so many times that the moment I see something going up, I instantly know that this is what I have to do, which is why it's so important that you practice these problems. Okay, and then this one, continues to swing as a pendulum. Calculate the time it takes between when the dart collides, here, to when it goes up, and then when it comes back down to here. Alright, so they want the time for a swing. So they want period. But, is this the full period? Well, let's see. A full period goes from amplitude to amplitude and back. This one is going from equilibrium to amplitude to equilibrium. This is only half the total period. So, the time is half the period of a pendulum, and if you look in the reference table, period of pendulum is 2 pi rad L over G, 2 plug and chug, 1.2 divided by 10. And we end up getting a time of 1.1 seconds. Alright, this was worth 2 points. Basically, 1 point for realizing that you had to do period. Basically doing this. and then 1 point for dividing in half. So the good thing is that if you didn't realize that this was only half of the period and you thought it was the full period, you would at least get partial credit. You would get 1 point, which is more than enough. Alright, now for this last part, it's asking a dart with more mass is launched at the same speed and angle. Dart collides and sticks with the same wooden block, and they want to know, would the period of oscillation increase or decrease, and then would the angle increase or decrease? Well, we can answer that second one right now. Second one's easy. It's going to end up staying the same. Now, the reason we know that is because if we look at the equation for a period, it's 2 pi rad L over G. Changing the mass and not changing speed, that's really all that's going to do is that's going to affect the speed that this has here and the height that it ends up going. It's going to change those values. We know that. But L is a constant value. Changing the mass of the object did not change L. G is a constant value. We're assuming that we're staying on Earth, so that's a constant value. So because T is dependent only on L and G, that means that, which are constants, that means that T must be constant. Alright. So you get 1 point for this, for saying it stays the same, and 1 point for the justification. Now, I know my justification isn't really written out that well, but again, I'm on an iPad with a stylus, and I can't really write properly with it, so too bad. Now, this part, saying what would happen to this angle. Alright, well, let's see. If we increase the initial mass, well, that doesn't change the initial speed of the object. But what that does do is change the initial momentum of the object. In fact, it gives the object more initial momentum, because mv. Make m higher while keeping v the same. Remember, that's the thing that makes that stays the same. And that means that the final momentum of the object is higher. Now, even though the final momentum of the object is dependent on the dart and the block, because these two are being added, the increasing m here, m of the dart here, increasing this value while also increasing that, isn't enough to keep this balanced. The velocity, the final velocity, also has to remain the same. Now you can double check this by plugging in numbers. So let's see, we had that the mass of the object was 0.02. Let's give it a big even 0.1. Oh wow, yeah, we're bringing it up to the block's mass. So that's 0.1 times the initial velocity v0, 0.1 plus 0.1 times v. So this ends up being 0.1 of 8.7 equals 0.2 v 4.4. 4.4 meters per second, which, if you remember from before, the old velocity was 1.4 meters per second. So yeah, increasing the mass here will increase the total momentum of the object before, which means that the velocity afterwards will increase. Another way to say it is that increasing the momentum before, increasing the mass of the dart while keeping the velocity the same, increases the initial momentum, which increases the final momentum, which increases the kinetic energy. Since you can actually rewrite the kinetic energy as p squared over m, I believe. You might want to double check me on that, but I believe that's what's going on. So again, you can see here that yes, even though the mass is increasing, the momentum is also increasing as well. And in this case, since momentum is squared, the increase in momentum is much bigger than the increase in mass. So doubling the mass also doubles the final momentum, but doubling squared. So yeah, kinetic energy will increase, which means that the final potential energy will increase. So the answer is increase. Again, 2 points, 1 point for the answer, and 1 point for the justification, however you want to do it, whether you want to use math or if you want to use logic. Alright, so again, practice this problem, make sure that you understand it, and let me know if you have any problems.